Okay, so today we are going to continue about diffusion. So this diffusion is basically mechanism that occurs for material processing. So including for solidification and also imperfection. When we want to make a solution, a solid solution, metal alloy, for example, the impurities, the impurities or the solute cannot just be directly spread all across the volume of the host material. Usually they have to be introduced at the surface, and then slowly they will penetrate into the depth of the material. And this penetration is done using the process of diffusion in solids. So in this chapter, we will address how does diffusion occur, why is it an important part of processing, especially to control defect, to control impurities. How can the rate of diffusion be predicted for simple cases? How does diffusion depend on structure and temperature? Basically, the definition of diffusion is mass transport by atomic motion. So the mechanism, if it were in gas or liquid, then it will be by random Brownian motion. Brownian motion, random, where usually in the high school it was just drawn like this. So when the particle is spreading and moving at very random, zigzag uh, zigzag motion, not always zigzag, but something like that. In solids, however, uh, the space between the atoms is not as wide or as big as in gases or liquids. So that is why the mechanism happens by vacancy diffusion or interstitial diffusion. In the vacancy diffusion, the vacancy move along the space of the solids, by uh, by hopping of the atom. In the interstitial diffusion, the smaller atoms is located in the space between the crystalline lattice atom will move around, in that space between the crystal atom. Interdiffusion in an alloy atom tends to migrate from regions of high concentration to the low concentration. So basically, this is the general law of diffusion. Similar like we have discussed also in sensor and measurement subject, the ions within the cell or cells to extracellular plasma will move according to their concentration. So this is then they do not require extra energy, unless if you want to move ions from the lower concentration to upper concentration to higher concentration, you will need additional energy and extra energy. So for example, if we have two materials located to each other like this, the left side is the orange type of atom, the right side is the gray colored atom. So originally it is like this, the concentration profile. So at the left side, it is completely 100% filled by the orange atom. On the right side, it's 100% completely filled by the gray atom. After a while, diffusion will occur. If we let them to migrate to each other, so there is there is no boundary between them. Then they will diffuse freely to other regions. So in this case, then, since on the right side there is a lower concentration of the the orange atom, this orange atom will diffuse to the right. The gray similarly will diffuse to the left. So after a while, they will have an equilibrium, something like this. So now there is some concentration on the right side of the material to some extent. Similarly, on the left side, where initially there is 0% concentration of the gray colored atom, now you will have some percentage of concentration over there. This is what we call as interdiffusion between two different materials in alloy. In elemental solids, on the other hand, it doesn't mean even though they are of the same material, they are of the same element, it doesn't mean that diffusion does not occur due to temperature or other things. atoms can still also move around. So they do not reside at the same location all the time. So for example, if we label some atoms within this material like this, CADV, atom C may move from this original position after some time to another position. D will move also to another position. A move to another position. B to another position. So this happens all the time. So therefore, maybe some things sometimes we see that a material like this, another solid material, whatever, yeah, wherever we see from outside, externally, like it is just a static material. In fact, there are some movements, some motions of atoms inside that material. Always there are motions and movement. Cannot be static because there is temperature, right? We live normally in room temperature, 25 degrees, 30 degrees Celsius, etc. This kind of motion of self-diffusion only stops when the temperature is absolute zero Kelvin. Yeah. So how does diffusion occurs? So diffusion can occurs, the mechanism, for example, as mentioned earlier, with a mechanism called as vacancy diffusions. Atoms exchange with vacancies, and this applies to substitutional impurities atom, where the impurity atom has similar size to the host atom. The rate of distribution will depend on the number of vacancies, yeah, as well as the activation energy to exchange. For example, initially we have this orange and gray atom, yeah, located next to each other. And then on the gray part of the material, we have one vacancy in the lattice crystal. So the orange atom may hop or may jump into that empty position, which will mean that the vacancy actually hopping towards the left, right? If we see it from the different perspective, then this left vacancy will be filled further by another orange atom above it, yeah, it will move to it, and then so that the vacancy then will move upwards to the upper position. Then the gray colored atom here, since it has a higher concentration on the right side compared to the left side, may then diffuse to the left side of the material, yeah, may hop or may jump to the left part of the atom, yeah, with the elapsed time. So this is actually a simulation. Yeah, it can be done in computer, yeah, how to simulate diffusion of the vacancy, interdiffusion across an interface. The rate of the substitutional diffusion will depend on the vacancy of concentration as well as the frequency of jumping. The frequency of jumping also will depend on other physical parameters like temperature, for example. So besides the vacancy diffusion like this, then there is also a mechanism called as interstitial diffusion. This is where the impurity is in the form of smaller atoms compared to the host atom. The smaller atom then can diffuse in the space between the host atoms. For example, here, initially the position of this atom, this small impurity atom is located here. Then after a while, it will move to this space between the host atom. See, we see here that since it does not depend on the hopping of the larger atom, on the existence of vacancy, this type of diffusion, interstitial diffusion, can occur more rapidly compared to vacancy diffusion. So diffusion is the mechanism, and then we can make use of this mechanism to for material processing, yeah, among others, like for hardening material, yeah, this hardening, yeah, to diffuse carbon atoms, yeah, into the host iron atoms at the surface to build steel, yeah, stainless steel, for example. Basically, it is an alloy of iron with carbon impurity and sometimes with other metal atom like chromium. This is an example of interstitial diffusion in a case of hardened gear, an iron that is being hardened by the diffusion of carbon atom. Yeah, results the presence of carbon atom will makes iron the steel harder. Another example of the use of diffusion in the processing and material processing is in electronics. You see that silicon in its nature in its natural characteristic basically is an intrinsic semiconductor. An intrinsic semiconductor does not conduct electrons when it is at room temperature. It only conducts electron when temperature is elevated. When it is heated, then the electrons will gain some energy to be able to move around. But in normal room temperature, usually very difficult for it to move around. So it means that the conductivity is low. One way to make a silicon to be conductive at room temperature is by introducing impurities, what we call as doping. So we can make we can make the silicon to be rich with negative charge carrier with electron, in which case then we will dope it with phosphorus. Phosphorus is located at column 5. Or otherwise, we can make the silicon to conduct hole instead, in which case then the active charge carrier is positive charge, the hole. In this case, we can dope the silicon with boron from the column 3 of the periodic table. So this is an example of computer chip, basically with light region here is silicon, and this is atom. We can deposit the phosphor-rich layers on a surface, after which then using thermal annealing or heat, we can make the phosphor on the surface to diffuse into the depth of the silicon. The length, the depth will depend on the concentration of this, the thickness of the P-rich layers on the surface, the temperatures, as well as the duration, time duration. So how do we quantify the amount or rate of diffusion? It is quantified using this formula. J is defined as flux, defined as the moles, or instead we can use mass diffusing per surface area per unit time. So if we are using in terms of atoms or moles, then we use mole per square centimeter per second, or if it is mass, kilogram per square meter per second. It is usually measured empirically to make thin film or membrane of non-surface area, then to impose concentration gradient, then to measure how fast atoms or molecules diffuse through the membrane. Okay, here we have the flux, so equals to the mass or mole divided by the area, square area per unit time. Okay, or 1/a dm dt. dm dt is the rate of how of mass that travels per unit second towards the depth of the material. Here, if we graph, here we have the mass diffused per unit time. This will be the slope. This dm dt is the slope, and divided by the square area to obtain the flux of the diffusion. We have what we call a steady state diffusion, in which the rate of the diffusion is independent of time. The flux will be proportional then to the concentration gradient across the depth of that material. Based on the fixed first law of diffusion, this is general law for diffusion in fixed law. So if we have here across this thickness, the material at x1 is C1, the material at x2 is C2. The material will diffuse from x1 to x2 according to this gradient. That is why J equals to minus D dC dx. If this is, for example, C at C1 is larger than C2, the material will flow from the lower x1 to higher x2. So that's why we put negative here. Okay, so because then the opposite of the diffusion is the direction of the diffusion is opposite to the coordinate. So if linear, then dc dx equal to delta c delta x equal to c2 minus c1 divided by x minus x1. Okay, so if this will flow into c2 if c2 is smaller than c1, so this value will be negative, right? And then if you put negative, then it becomes positive. So J is positive. Okay. The D here is the diffusion coefficient. For example, in the production of chemical protective clothing, let's say, for example, for APD, alat pelindung diri, self-protecting device, SPD in English. Methylene chloride is a common ingredient of paint removers. Besides being an irritant, it may also be absorbed through skin. When using this paint remover, protective gloves should be worn. Now, if butyl rubber glove with 0.04 centimeter thickness are used, so for the 0.4 millimeter, what will be the diffusive flux of methylene chloride through that glove? If the diffusion coefficient is given, let's say 110 times 10 to the power of minus 8 centimeter square per second, and the surface concentration is given, C1 is 0.44, the concentration at the outer layer of the glove is 0.44 gram per cubic centimeter. Concentration at the inner layer of the glove is 0.02 gram per cubic centimeter. Then, assuming linear concentration of the gradient, the concentration decrease linearly with thickness. So then we can calculate J equal minus D dC dx. And since it is linear, we can approach it as delta C over delta X. Okay, so D is given from here, 110 times 10 to the power of minus 8. C1 is given 0.44 gram per cubic centimeter. C2 is also given 0.02 gram per cubic centimeter. The difference in the position is the thickness of the glove, which is 0.04 centimeter. Okay. So then we can calculate J, the flux, equals to minus D, minus 110 times to the power of minus 8, times delta C, this minus this, 0.02, minus 0.44, divided by 0.04, the thickness. Then we will obtain the flux of the the material, methylene chloride is 1.16 times 10 to the power of minus 5 gram per square centimeter per second. So here, then you can calculate how long that glove should be replaced, before a contamination is becoming dangerous. Okay. So you can calculate this multiplied with the time, the duration of your work with that glove and with that paint. From there, then you can calculate the duration where you need to replace that glove. Okay, then diffusion and temperature. The diffusion coefficient here, D, actually is not something constant. It can also increase with increasing temperature. Okay, and the new diffusion coefficient can be calculated using this formula: E equals to D0 exponent minus QD over RT. The D0 is the pre-exponential diffusion coefficient. The QD is the activation energy. This is similar, maybe no, not the same with the activation energy which we have learned earlier. R is the gas constant, and T is absolute temperature in Kelvin. So from here, D has exponential dependence on T. The larger the temperature, then the D will decreases. The D will decrease because this one is minus. The D will decrease. This is 1000 Kelvin per in temperature of 1 over T. 1 over T. Sorry, not like that. With increasing temperature, actually the D increases. You have to look at backwardly. Because here with to the right here, the temperature is decreasing because this is expressed in 1 over T. In 1000 Kelvin. Okay, so here we see that the value for interstitial diffusion is larger than substitutional diffusion, as we have learned in the previous slide, because the space in the interstitial in the carbon in iron, carbon is much smaller than iron atom. That's why it can seep through and move around in the space between the iron atoms. Aluminum, in the other hand, needs to substitute the vacancy that is there in the crystalline lattice of the iron. So aluminum in aluminum, or iron in alpha iron, or iron in gamma iron, the substitution, this is self-substitution, self-diffusion. The value of the D is smaller than interstitial, the D interstitial for carbon in alpha iron or carbon in gamma iron. So because it means that this carbon is larger rate of diffusion into the iron. For example, at 300 degrees Celsius, the diffusion coefficient and activation energy for copper in silicon are given here. The D is 7.8 times 10 to the power of minus 11 per square meter square per second. The activation energy, QD, is given equals to 41.5 kilojoule per mole. You are asked to calculate the diffusion coefficient at 350 degrees Celsius. Okay, so this is the data where D increases with increasing temperature in the exponential term, where we can transform into natural logarithmic, ln D here versus 1 over T, which will become a linear line, decreasing linear line. So natural logarithm of D2, the D at the 350 degrees equal the natural logarithm of D0 minus QD over RT2. And similarly, natural logarithm of D1 at 300 degrees Celsius equals to natural logarithm of D0 ln D0 minus QR minus QD over R times 1 over D1. So then from here, we can calculate D2 by subtracting D1 here from ln D2. Ln D2 minus ln D1 equals to minus here Q dr over R 1 over T2 minus 1 over T1. And this equals to natural logarithm of D2 over D1, from the properties of natural logarithm or logarithmic operator. Then, based on this, we can calculate exponent D2 over D1 or D2 over D1 equals to exponent of minus QD over R, and inside the bracket 1 over T2 minus 1 over T1. T1 is 300 degrees Celsius, which is equal to 573 Kelvin. T2 is 350 degrees Celsius, equals to 623 Kelvin. So the D2 can then be calculated equals to this D1, the D1 here, exponent minus 41,500 joule per mole over the R, this is the R, the gas coefficient, times 1 over 623 Kelvin minus 1 over 573 Kelvin. So then we obtain D2 to be 15.7 times 10 to the power of minus 11 meters square per second. So if you compare here the two diffusion coefficient, this is D1 and this is D2, in the higher temperature, 623 Kelvin, the diffusion coefficient becomes bigger, right? Increases. So it means that the material, the impurities can penetrate, even in this case is copper, and the host is silicon. The copper can penetrate faster into the silicon host material. We can also have non-steady state diffusion. In this case, that the concentration also varies with the thickness. Yeah, the thickness. So the concentration of the diffusing species is also a function of both time and position. So in this case, we cannot have any more simple differential equation. We have to use the fixed second law using partial differential equation. So dou C dou T equals to the diffusion coefficient D times dou square C dou X square. Okay. So this is an example. The copper diffuses into a bar of aluminum. Okay, this is the surface copper. We have the concentration of the copper ion at the surface, CS. There are also pre-existing concentration of copper along the aluminum bar, okay? And that concentration is drawn here in this graph. Yeah, so at T0, this is at T0, all the copper are completely at the surface. This is CS. Then when time increases T1, some copper starts to diffuse along the thickness. Then at T2, more copper diffuses, okay, so that even at the same thickness, we have then larger concentration of copper compared to at T1. At T3, then a longer time, at T3, the concentration profile becomes like this. Okay, so at T0, the concentration equals to C0, yeah, which is here for 0 until X, for X between 0 and infinity. At T larger than 0, the concentration is CS, the same, still the same CS for X equals to 0, which is at the surface of this aluminum bar. And the C is C0 for X equals to infinity, and from infinity distance from the surface. So the solution for partial differential equation like this, yeah, second degree, yeah, second order partial differential equation will be in the form of error function. So then the concentration as a function of X and T as a function of the depth from the surface as well as time compared to the initial concentration at that bar over the initial difference between the concentration at the surface and at the bar equals to 1 minus error function X over 2 square root dt here. Okay, so Rz here is the error function which is defined here. This is one of the transcendental function. I think you studied this as well in calculus. 2 over square pi integral from 0 to z exponent minus y square dy. So the error function values are given in table 5.1 in the textbook. It is located there. So usually we don't really calculate, but we just look at the table and then we estimate the value. The value, the error function value is given, then we estimate the z value is on that. So this is an example of non-steady state diffusion. Yeah. An FCC phase center cubic iron carbon alloy initially containing 0.28% of carbon. Yeah, so this is the initial concentration, the C0 inside that iron carbon alloy. It is carburized. Carburized means that at its surface, it is further exposed to carbon at an elevated temperature and in an atmosphere that gives a surface carbon concentration constant at 1 weight%. Okay. If after 49.5 hours, the concentration of carbon is 0.5 weight% at a position 4 millimeter below the surface, determine the temperature at which the treatment was carried out. So we are asked to determine the T temperature. So using the equation written in the previous slide, Cxt minus C0, C0 is known here, 0.20%, Cs is known here, 1%, yeah. Then D is given usually as in the form of data. Time is given here 49.5 hour. The X here is 4 millimeter, yeah, 4 millimeter. So T is 49.5 hour. Usually we have to convert into second. Cx is known, 0.35% here. Yeah, the eventual concentration at 4 millimeter. C0 is 0.20% from here. Then Cs is 1%. Cs here is the concentration of the carbon being the carburized carbon, yeah, which is at the surface of the iron. Here, yeah, the 1%. The X is 4 millimeter, so it's given 4 times 10 to the power of minus 3 millimeter. So we just insert this into the formula, yeah, 0.35 minus 0.20 divided by 0.20 by 1 minus 0.20 equals 1 minus error function. X is 4.10 to 4 millimeter divided by square root divided by 2 times square root of D times T. T is known here, 49.5 hour. So we'll calculate first the D, later we calculate the based on D0. Yeah, the result is the error function Z is 0.8125. So now we must determine from the table. This table is given, usually it is in the textbook, it is there as table 5.1. The value is 0.8125, and then we can interpolate. Yeah, so the given value in the table, so similar like when you are interpolate the value of logarithmic, yeah, maybe in the elementary school or junior high school. Of course, if we use calculator, we can also use calculator. So the Z is 0.90. The error function is what is being written in the table is this value and this value, while the given value from the calculation earlier is 0.8125. So now we have to estimate this value Z. So we can use interpolation, from which we obtain Z equals more or less 0.93. Okay, and this 0.93 equals to the value of this X divided by 2 square root of dt. Okay, so from here D equals to X squared times 4 times T X squared divided by 4 Z squared times T. Okay. From here, then we calculate further. We put X is 4 millimeter square divided by 4 times the Z is from here 0.93 square times the time here 49.5 hour, and then we have to convert this first into seconds. Yeah, so multiplied by 3,600 seconds per 1 hour. So here we obtain 2.6 times 10 to the power of minus 11 meter square per second. This is the diffusion coefficient. The question is what temperature? So we have to compare this with the diffusion coefficient at room temperature, yeah, to get the temperature. So to solve for temperature at which D has above value, we rearrange the equation from the previous slide also. T will be equals to QD, the activation energy, divided by R, the gas constant, times ln natural logarithm of D0 minus natural logarithm of D. The diffusion coefficient of carbon in FCC at the room normal temperature, 2.3 times 10 to the power minus 5. Activation energy is also known. So based on this, we can calculate T to be 1,300 Kelvin or 1,027 degrees Celsius. This is the process, the temperature process where this carburization occurs. Yeah. And then to reach 0.35% with weight percent of carbon at 4 millimeter below the surface. Yeah, this is non-steady state diffusion. So far, understandable? Yeah. Any questions? Another example here. So Methylene chloride is a common ingredient of paint remover. This is the same like before. If but butyl rubber glove for 0.4 millimeters, so the same as before as well, are used, what is the breakthrough time? How long could the glove be used? This is actually the question that I asked earlier. We use before the methylene chloride reaches the hand. So the diffusion coefficient is known, 110. The coefficient, this is the diffusion coefficient of methylene chloride inside butyl rubber glove, 110 times 10 to the power minus 8 square centimeter per second. If we assume linear concentration gradient, yeah, something like this. So TB, the time will be equal to L squared divided by 6D, 6 times the diffusion coefficient. Then we obtain the L, X between 0.04 centimeter, 0.4 millimeter. The D is known. So the time required to reach the skin is 4 minutes. 0.04 centimeter square divided by 6 times 110 times 10 to the power minus 8 square centimeter per second. Yeah, so it's quite quick, yeah. So time required for breakthrough about 4 minutes. So in summary, diffusion is faster for open crystal structure where the structure is open, there is a grain boundary, yeah, then the impurities can diffuse quicker there. And faster also for materials with secondary bonding, for example, with hydrogen bonding, van der Waals bonding. Faster for smaller diffusing atom like carbon diffused in iron, for example. And also when the material has lower density, it means that many space between the atom in the crystal. That is why diffusion will occur faster for BCC in BCC hosts, yeah, compared to in FCC hosts, yeah, or HCP, that is hexagonal closed pack hosts. Diffusion is lower for when the host material is closed pack structure, or when the host material is with having covalent bonding. Okay, because then it is not easy to kick out the atom, if in the substitutional case of diffusion, not kick out one atom that it moves to another position. It is not that easy. Also, it is lower when the impurity or diffusing atom is larger. Then in higher density material, it is also slower, yeah, because the material means it's very packed, only small space between them, and they are already in the most stable state of the structure. So it's not easy for other things to diffuse, or even between them to diffuse, to have self-diffusion is not that easy. Okay, any questions so far regarding diffusion?
No, sir.
No? Quite clear, yeah? So we can have quiz also.
Jangan gitu, sir.
For 2 chapters ya.
Yang dia aja nggak mau tuh.
Kenapa?
Kalau 2 1 hari tuh, aduh, sir, gimana ya, sir ya?
No, I mean